Okay, so this is the video about our propeller design process done for the class MEC 533. I'm Louis.
I'm Chad.
I'm Orlando.
I'm Alejandro.
And basically we're just going to go over every step of how we took this design from the design step to a final manufactured part. We're given a series of design objectives to try and reach during the design of the propeller. The first of them was to have a specific static thrust at a specific RPM that was 0.2 newtons at 5,000 RPM. And secondly, we're tasked to try and have our maximum efficiency at a given airspeed and at a given RPM. And those two numbers were 5 meters per second and 9,000 RPM.
We also decided to impose an elliptical thrust distribution, as this would minimize the induced drag, as we've seen in class. And this would then help us maximize our efficiency because we have less drag per unit thrust we produce.
So we also decided to keep the efficiency constant along the blade because we thought that would keep the resultant force on the blade at a constant direction from the root to the tip. And this we thought would, increase the efficiency of our propeller. And when we ran simulations, it actually showed that this was a good thing to do. Okay. So to generate our first design, we used the blade element theory combined with some data that we pulled out of the software XFLR. So in this slide, you can see a diagram of the basic geometry of blade element theory. So as you can see, there's a velocity triangle, which is composed of the incoming flow velocity, u infinity. Then there's the velocity component due to the rotation of the propeller. And then there's the resultant velocity, which is u1. Then the forces are represented by the lift force, which is parallel to the wind velocity. Then there's the drag force, the lift, which is perpendicular to the wind velocity, the drag force, which is parallel to the wind velocity, and the thrust instead is perpendicular to the rotation axis. So here are all the necessary angles that we'll be talking about later in the design. So this is a flow chart of the process that we use to get some results, to get some design criteria that we could use to make a first kind of like design of a propeller. So we started by enforcing the static thrust condition, which was that the thrust must be 0.2 newtons at 5,000 RPM. And combining that with the condition that we wanted was that the thrust distribution would be elliptical. So by combining those two, we get a lift distribution over the whole blade. Then we made the assumption that the lift coefficient must be equal to 1 over the whole blade. That's just kind of like a reasonable assumption, and it'll be corrected later. But thanks to this assumption, we can now get a chord length at every control point that we've defined across the blade. Then we can get the Reynolds number under the max efficiency conditions. So now we're looking at what's the Reynolds number at each control point when the wind speed is 5 meters per second and the rotation is 9,000 RPM. Now using the software, we can find the optical NACA profiles at each control point. And then by enforcing the constant efficiency condition, we can also find the pitch angles at each control point. Now, again, we can go back to the software. We can find the actual lift distribution at each control point. So that way we correct our initial assumption and we can adjust the chord length. At this point, we could iterate the whole process and keep doing it until our values converge. But what we saw is that after one pass, the chord lengths actually haven't changed much. And so we used the values that we had to move on to the simulation, which will be explained by Chad later. So this slide just kind of shows the results that we got after this first theoretical analysis. And on the left, there's a general diagram of the propeller with the radius and the position of the control points. and yeah, that's about it. So our expected efficiency based on this theoretical analysis was about 74%.
So after we finished designing our propeller based on plate element theory, we transferred it to JPlate, which is a numerical solver that lets you approximate different propeller properties. And we used that to estimate the performance of our propeller for the target design conditions. So as you can see here, we estimated our thrust for static conditions at like 5,000 RPM. We couldn't get an actual value because you need a wind velocity to use, but interpolating from the thrust graph you see here, you can see that we were pretty close to our design target of 0.2 newtons. For efficiency, however, we noticed that we weren't optimizing so as to have the peak at the test conditions, but we were actually maximizing the value of the efficiency of our test conditions, and this resulted in us having a peak at the wrong spot, and that's something we fixed with the rest of our design process. So we ended up modifying our design so as to optimize the equation that was given for creating the propellers. We had to pitch down the propellers so as to have the peak of efficiency at the lower value of advance ratio. This dropped our thrust because we had less lift, and so we had to increase the blade size. We also made the cord thicker because we were worried it would break. And we then picked again the most efficient foil here. We also dropped the condition of keeping efficiency constant along the whole blade because the root had a way lower efficiency than the rest, and efficiency was instead kept constant for the 5 sections after the closer to the end, and this gave us better results. So after significant trial and error, we ended up finding a propeller that matched all our design targets. So this has a thrust slightly under the requirement, but it's still really close. And efficiency that's almost exactly at the peak we want. It's somewhat lower than the efficiency we had for our initial propeller, but at least it's at the right spot.
Okay, so for our CAD design, basically the first step was to summarize all our design parameters. This is the cord length, the twist angle, and the airfoil at each location of along the radius. The second step was basically to import the points and curves to Solid Edge. Solid Edge was the CAD package we used to design our propeller. And you can see in the picture, we import the curves, we import the points and curve, and we just have to rotate each airfoil section and each section with its respective twist angle. The step 3 was basically repeat the process in step 2 by creating parallel planes along the radius and again rotating each profile at the respective angle, as you can see in the picture. The final step was to extrude by sections each one of the profiles along the radius and designing the hub. The final design propeller, the CAD propeller can be observed in the picture in the right.
Now onto the performance analysis. So here we have a graph that shows the efficiency of the propeller over the range of RPMs it was tested for. So we can see immediately that the peak is not reached at 9,000 as designed. The efficiency keeps increasing past the maximum RPM tested. But we can see that we did reach an efficiency of around 30%, around 9,000 RPM, which was one of our design objectives. And also we can see that we have 2 curves here, the experimental and blade element theory curves. So evidently the blade element theory curve uses blade element theory to calculate the efficiency and makes the assumption that the
induced velocity and the induced angular velocity and the induced wind velocity are ignored, basically.
while the experimental curve makes no such assumption and simply uses the thrust of the thruster and the power of the motor to determine efficiency. So we can see that making this assumption doesn't have a big effect.
Okay, in this graph, basically we can see the distribution of the angle of attack alpha along the radius of the propeller for different RPMs. We can see basically that at low RPMs, the alpha distribution is going to be almost negative along the radius. As we increase our RPM, these values start increasing as well, reaching positive values. This explains also basically why at low RPMs values we obtain negative thrust. As we increase RPM, our propeller starts to have a positive distribution of alpha. That means that we are increasing our lift, or in this case our thrust, as we move along in the radius.
So in this video, we can see the propeller actually functioning in the air tunnel. So in this test, we can see fairly well certain misalignment in the mounting of the propeller. We're thinking that this probably induced more noise and vibrations than would otherwise have occurred in the propeller, which obviously affects efficiency and the ability of the thruster to work without causing noise in the thrust curve, which is reflected in our results. So now here in this close-up, we can see the manufacturing defects in the prop a bit better. So first of all, along the edges, the thin edges of the blades, we can see some chipping, which was somewhat alleviated using sanding, but might still have had an effect on the efficiency of the blade. And also, in the mounting hole, we can see that it is, first of all, much larger than was designed for. This is because during the 3D printing of the part, this section of the part was filled in instead of being an empty hole, which required some drilling and filing to make it able to fit in the mounting screw of the motor. So obviously this caused the hole to be a little bit eccentric, which obviously introduced eccentricity in the rotation of the propeller and also had an effect on noise and the efficiency.